Hey everyone, welcome to this video. We're going to talk some about the expansion coefficient and the relationship between CP and CV. Okay, so before we get to how CP and CV are related, we need to first talk about some things we haven't talked about yet, like how does internal energy change at constant pressure? Okay. Right, what is, say, the change in internal energy with respect to change in temperature at constant pressure, right? Now we know the differential for internal energy, right? That some small change in internal energy is related to the slope of, with respect of u with respect to t, right, times dt, plus some small change in u with respect to some small change in v times dv, right? So we know that, okay? We can rewrite that as just CV dt plus pi t dt, right? Just using the definition of CV and pi t, okay? Now, if we take the derivative of this entire relationship with respect to temperature at constant pressure, right, then, then our du becomes del u del t at constant pressure. We then have CV dt. Well, the derivative of this respect to t, right? You get dt dt, so those cancel, so you're just left with CV. And then we're left with pi sub t, and then del v del t at constant pressure, right? What is the change in volume with respect to change in pressure, temperature at constant pressure? So the expansion coefficient, right, is going to be related with this change in volume with respect to change in temperature, constant pressure. Okay, so it is defined here. So alpha is the symbol for the expansion coefficient, and this is something that is determined, right, through experiments and things of that nature for all sorts of different materials, not just thinking about for gases, but liquids and especially solids. Okay, right. And so the expansion coefficient, right, is 1 divided by volume times how the volume changes with temperature under constant pressure. Okay, and so the fact that it has this 1 divided by the volume term in there makes it a kind of percent change, right? So the expansion coefficient is a kind of the percent change in the volume with change in temperature. Okay. And that makes it more of an intensive quantity, right? So it's not going to depend on the total volume, right, as to what that change is. Okay, and this is relevant for all sorts of material applications, things like that, right? But basically thinking, right, for some material, how much is it going to expand or contract as it heats up or cools down, right? If you have certain materials that go into some machine, right, that's going to experience some extreme temperatures, right, you need to make sure that how things fit into some other thing and how it's created is not going to break down under high temperatures, right? So at high temperatures, right, things expand, right? So if you have something that fits nice and smooth into some other spot, right, but then you're using some material that has a large enough expansion coefficient that at the temperatures you're working with, right, that volume is going to change by by some significant amount, right, to where now it no longer fits, right, then your machine is going to break, right, it's going to break down. So right, and so this is something that is often known for a lot of materials and measured, okay, depending on their applications, okay. And so if we use that expansion coefficient, we can substitute that in, right, because V, right, so if I multiply V times alpha, right, then I'll just get, all right, the dV dt at constant pressure, right. And so V times alpha times pi sub t is that last term, right? And so for a gas or any material for that matter, the change in internal energy with respect to change in temperature at constant pressure, okay, is related with CV plus alpha pi sub t V. Okay. Now for an ideal gas, right, pi sub t is 0, so it's just still CV, right? And that's why again, for an ideal gas, changes in states, right, we always just think of CV delta T. Okay. Right. We want to derive what the expansion coefficient is for an ideal gas, right? We need to think of what volume is in terms of temperature, and then we plug that in to our derivative, right? So dV dt, so the derivative, right, is just going to be nR divided by P, and then you're going to be left with nR divided by P divided by V, right? Which is just going to equal 1 divided by the temperature, okay? Right, so alpha for an ideal gas, right, is just 1 over T, okay? Right, now the next step we need to look at is looking at enthalpy and looking at how enthalpy is changing with constant volume. But to do that, we first need to do what we did with internal energy and find the total differential of enthalpy, okay? And so, right, we're going to take enthalpy, think of it as a function of temperature and pressure, and write dH is del H del T dt plus del H del P dP, right? So it's the same thing we did with internal energy, right? It's just enthalpy is thought of as a function of temperature and pressure, not a function of temperature and volume, okay? Right, we know what del H del T at constant P is, right? That's Cp, right? That's constant pressure heat capacity. So the question is what is del H del P at the constant temperature? Okay. Right, and to do that, we're going to be using the Joule-Thomson coefficient and some rules of partial derivatives. Okay, so we'll first use the chain rule to note to the fact that -1 is equal to del H del P at constant temperature times del P del T constant enthalpy times del T del H at constant pressure. Okay, so this chain rule here applies for any state function, any exact differential. Okay, partial derivatives work in this way, and this then rearranging it tells us that del H del P at constant temperature is related with -1 over del P del T constant enthalpy del T del H constant pressure. Okay, we're then going to invert one of these partial derivatives. Okay. So we'll invert both of these, right? So we'll get del T del P at constant enthalpy and del H del T at constant pressure, okay? Right? Because basically what it just is, we do 1 over x divided by y is equal to y divided by x, right? That's all we used, okay? And then we notice, right, del H del T at constant pressure is just Cp, and then we have del T del P at constant enthalpy, which is going to be this mu here, which we're defining as the Joule-Thomson coefficient, okay? Right, and so this is measuring how temperature changes with the change in pressure under constant enthalpy, okay? Right, this is a very tricky experiment to do to actually measure the Joule-Thomson coefficient for a material for a gas, right? Because holding enthalpy constant is not something very easily done, right? Takes very precise setups to make sure and ensure that there is no enthalpy change in your system, okay? But if you do that, you can measure the Joule-Thomson coefficient for a material, okay? But we'll note here that just looking at the sign of this, right, that if I have the Joule-Thomson coefficient is del T del P, right, at constant enthalpy, right? So if that's less than 0, then as say, increase the volume of my gas, the pressure is going to decrease, right? Because of this inverse relationship, and the temperature will increase, right? And that's when repulsive forces are going to be dominating, okay? But if the Joule-Thomson coefficient is greater than 0, then as my volume increases and my pressure decreases, then the temperature is also going to decrease, okay? And that's when attractive forces dominate, okay? Right, for an ideal gas, then this thing is equal to 0, okay, right? And you can think about this as we talked about kind of the internal pressure in terms of attractive versus repulsive forces and right, depending on where your average value of distance is, say on your potential energy surface, right, can impact then how the temperature is going to change, right, the kinetic energy and such of your material is going to change, the change in volume and a change in pressure. Okay, so plugging this right back in, we're going to be trying to look at again what is del H del P, and we see that that's negative mu, this Joule-Thomson coefficient, times Cp. Okay, and so now this is the total differential of enthalpy, right? And so the next thing we're wanting to look at is how does the enthalpy change with temperature under constant volume. So again, we're just going to take the derivative of this entire thing, right? Do del T under constant volume of everything here, right? And that just gives us Cp minus mu Cp del P del T under constant volume, okay? And again, we can use this chain rule for partial derivatives, okay, for del P del T under constant volume to write it in terms of del T del V under constant pressure and del V del P under constant temperature, okay? And okay, and so this was from that previous slide, right? The chain rule solve this, right? Now we're going to flip one of these, right, and write it as del V del T under constant pressure, right? And if you recall, that's related with our expansion coefficient, right? Expansion coefficient, it was 1 over volume times how the change in volume is affected by a change in temperature under constant pressure conditions, okay? And so we're going to find one other thing called kappa sub T, okay? The isothermal compressibility, okay? So kappa sub T is our isothermal compressibility, right? Isothermal, constant temperature compressibility, right? And so this again is defined as a 1 over volume term. Now there's a negative sign in here, so just be in mind that it's defined with this negative sign, okay? So kappa sub T is negative 1 over the volume times del V del P at constant temperature, okay? All right, and this negative sign is necessary because of kind of the inverse relationship between volume and pressure and things like that to make it so kappa sub T is actually a positive quantity, because that derivative del V del P is a negative value, and so to ensure that isothermal compressibility is always a positive term. At least typically it's a negative value, and so it should be positive, okay? Right, and so what this is related with, right, isothermal compressibility, right, that's very important for a lot of material, like say the material you're using in building, right? If you're building something, right, you're building a huge skyscraper and you're using certain support beams for that skyscraper, you want to know, you know, those beams on the bottom level, right, that are holding a bunch of weight from upper levels, okay, it's going to have a lot of force, a lot of pressure on it, and you want to know, is it going to compress some? And if so, by how much, right? Because that is going to matter, right? How much that material is going to compress, right, underneath that weight, okay? Can make a big difference in the stability of that structure, okay? So isothermal compressibility is also a very commonly used thing in engineering to understand how the volume changes with material under pressure and constant temperature, okay? So using those relationships, we find that del P del T under constant volume is just equal to alpha divided by kappa sub T, okay? And so again, the kappa sub T, right, is that definition of isothermal compressibility. So plugging this in, right, what we find is that the change in enthalpy with respect to change in temperature at constant volume, right, is equal to Cp minus mu Cp del P del T. And then using what we found for del P del T, we get this term here, right, and then kind of simplifying it slightly by pulling out the Cp, we finally get that the change in enthalpy with respect to change in temperature under constant volume is related with Cp minus alpha mu over kappa T, okay? Right, and so this is a little bit more complicated looking, if you will, than that of how the internal energy changes with temperature under constant pressure, right? but it's a somewhat similar expression. And note here that that second term, that minus alpha mu over kappa T, right, that term is 0 for an ideal gas, because mu, the Joule-Thomson coefficient, is 0 for an ideal gas. Okay, and so also look here at what the isothermal compressibility is for an ideal gas. Again, we use the ideal gas law and just take the derivative of volume with respect to pressure. Okay, right? And when you do that, you get minus nRT divided by p squared, right? And that's multiplied by -1 over volume. Okay, you can simplify that down to just 1 over p. Okay, because what you'll end up with, right, is nRT over Vp times 1 over p, right? Well, nRT divided by Vp, this here just equals 1, right? It's our ideal gas law, right? Pressure times volume equals nRT, right? So that just equals 1. So it just simplifies down to 1 divided by the pressure, okay? So that is the isothermal compressibility of an ideal gas, okay? So finally, after all of this, we can finally look at how CP and CV are related, okay? So we start off, right, with just what are the definitions of CP and CV, right? And then we're going to plug in for enthalpy, right? We're just going to plug in the fact that enthalpy is defined as the internal energy plus PV into there to get del U, del T under constant pressure plus del PV, del T under constant pressure minus del U, del T under constant volume, okay? Right, it's constant pressure, so pressure just gets pulled out here, right? We've solved for what this is already, okay? Right, and note that this is just equal to CV, okay? And so, right, what we're left with, right, is when we take del U, del T under constant pressure minus del U, del T under constant volume, right, we are just left with this term alpha pi sub T times volume, okay? And then we still have this del V, del T under constant pressure term, right? But recall, right, that our expansion coefficient alpha is defined as 1 over V times del V, del T, okay? So this P times del V, del T just simplifies down to P V times alpha, okay? And so we can simplify this a little bit, pull out an alpha times V from both these, right? And you have alpha V times the pressure plus the internal pressure, okay? Well, what we'll show, and we'll need to show this later after we talk about entropy, right, is that this pressure plus internal pressure is equal to temperature times del P del T under constant volume, okay? And we know del P del T under constant volume from earlier in this video is equal to alpha divided by kappa sub T, right? The expansion coefficient over the isothermal compressibility. And so P plus the internal pressure pi sub T gives us alpha T over kappa sub T, okay? And so finally plugging that in back up here, okay? We get that CP minus CV is equal to the the expansion coefficient squared times volume times temperature divided by the isothermal compressibility, okay? And that is our final relationship between CP and CV. Now note here that we did not make any assumptions about ideal gases, about it being a gas even, right? This is true for solids, liquids, gases, plasmas, whatever phase, whatever state you're in. This is the relationship between CP and CV. Okay. Right. Now again, if we're talking about for an ideal gas, right, if we recall what the expansion coefficient isothermal compressibilities are, right, that they're 1 over temperature and 1 over pressure, we can just plug that in, right, to get our relationship that CP minus CV is just equal to NR, okay? So that relationship we've used so far, right, we get from this expression for an ideal gas, right? Now in general, right, in order to calculate CV from CP or CP from CV, right? For gases, you need to calculate those expansion coefficients and isothermal compressibilities and such, right, to get that difference. Okay. Now we'll note that for liquids and solids, Cp and Cv are very similar to each other, right? And it's usually just because the expansion coefficient and isothermal compressibilities are both usually small. Okay. And so, right, you have these two very small numbers, right, which you think take the ratio of two small numbers, maybe isn't necessarily a small number, but the thing is you have alpha squared, right? You have the isothermal, the expansion coefficient squared divided by the isothermal compressibility, so that ratio ends up typically being a very, very small number, and so often the heat capacity difference between constant pressure and constant volume for liquids and solids is very minuscule. Okay. Right, so this video here is to show you where these relationships come from, right? It's a little bit of a dive into more advanced thermodynamics, right, and thermal chemistry, and how one actually tries to derive certain relationships between certain things that we can measure and understand in lab, okay, by using partial derivative rules, some advanced multivariable calculus and such, okay, right? But you don't need to rederive these relationships, right? You don't need to necessarily even remember how we did this, okay? But you need to be comfortable to use this relationship between Cp and Cv, right? And to kind of understand what these different terms are: internal pressure, expansion coefficient, isothermal compressibility, and Joule-Thomson coefficient, okay? And so that's going to be it for this video. It's kind of a long one compared to some of the other ones, okay?